Okay, so I sent you all a notebook yesterday. I don't know how many of you had a look. Anybody have a look? Yeah. Did it work? Do you have a look? Why not? Still don't have Mathematica. Now you guys had better install it. Yeah. You know, there's a guy called James Joyce. He wrote a book called Finnegan's Wake. Now nobody could really understand what he wrote. It was very difficult. So they asked him, why did you write such a difficult book? So he said, the reader should put in as much effort in reading it as I put in writing it. So then don't come back later and say this was not clear and that was not clear, because I think I'm trying to take a lot of effort to make these topics understandable, and then if you don't keep up with me, it really is your problem. Okay. So the other day we had done this KK bar mixing business, and then we found these two states which were called K1 and K2, and we wrote them as CP eigenstates, and then we showed that if CP is a good eigenstate, then one of them, which is K1, can only decay to 2 pions, whereas the other one, which we call K2, would decay only into 3 pions. Okay? So that was a claim, but then experimentally it was found that even the second state could decay into 2 pions to reduce the branching ratio. So then it no longer makes sense to call them K1 and K2, because the names K1 and K2 are given if they are CP eigenstates. But because CP is violated, it no longer makes sense to call them K1 and K2, and that's the reason we have given new names to them. And what are the names that is given to them in light of this fact that CP is violated? What are the names that is given? Right, KL and KS, S for short-lived and L for long-lived. So that is what we had. Then there was another puzzle at that time, and I'll let you figure this out. So there's something called the theta tau puzzle, which was resolved by Yang and Lee. Yang and Lee. And your homework problem is to figure out what this puzzle is and in what way Yang and Lee actually resolve this particular problem. Similarly, if C is a good symmetry, then phi 0 going to gamma is allowed, but phi 0 going to 3 gamma not allowed. And this is okay because this goes through the anomaly. This is not a weak decay, and so this is allowed. Okay. So this is the kind of little facts that you need to know about C violation, P violation, and CP violation, etc., etc. So this K0 bar system was the only known example of CP violation for a long time, until the decade of 2000, where the B system shows ample CP violation. Okay, so that is K0 bar, and for a long time, of course, before the standard model came about, people thought of various reasons why there may be CP violation, and Wolfenstein proposed something called super weak. So all these were allowed in the framework of ideas and logic. And then there are other schemes called milliweak. And it turns out that standard model actually is a milliweak CP violating system. And you can have CP violation in the standard model only with a minimum of 3 generations. And this comes about because of the full CKM matrix. So a friend Nick the other day was asking, why do you call it sine theta C, cosine theta C? Well, if you had only two generations and then you had mixing between the D and the S quarks, then you can say that one of them has an amplitude that's proportional to x, the other has an amplitude proportional to y, so x squared plus y squared is equal to 1. So alternatively, you can just call it sine theta C and then describe it in terms of an angle, which is the Cabibbo angle. So that was for two generations. And once you write it down in terms of this kind of a mixing matrix, then with this kind of a property, unitary matrix with some additional constraints, it's not the most general unitary matrix, and it can be readily generalized to a larger number of generations, and that's how we get the full Kobayashi-Maskala. Yeah. Yes. Yes. No, not U. DSB. It gives a mixing between the DSB. So it is the strength of the interaction between U and D, U and S, U and B, or C and D, C and S, and C and B, or T and U, or T and. So it's a mixing of the quarks in the down sector. Okay, that's what the mixing takes place, and at the vertex you get these factors associated with the transitions of U to D, U to S, U to B. Okay, or C to U, C to S, C to B, and finally T to U, sorry, T to D, T to S, and T to B. Okay. Physical meaning of milliweek is a good question. I don't know exactly what the definition is, but there's a good review, a paper, and many books edited by Kleinknecht. You can look at, you can just Google Kleinknecht and have. There are also a couple of very good books on CP violation. There's one by I. Biggie, and then there's one by Lavura, Branco, and Silva. So I of course have my own copies of all these things, and if you want to consult them, you can come, borrow them, read them in the corridor, and then give it back to me. Okay? But presumably it's all available on LiveGen. So anyway, since I'm over here, and since quarks are Dirac particles, I don't think anybody would dispute that quarks are Dirac. Why are they Dirac particles? In contrast to what? What else can they be? Majorana, yes. No, spin of course. Spin half. But these are Dirac in contrast to, let's say, neutrinos. What can they be and why? But why is it not possible for quarks? So these are all, you're giving a circular argument. What is the fundamental reason why a quark can't be anything but a Dirac particle? What is the primary difference between a neutrino and a quark? Of course, they participate in strong interactions. Forget about that for the moment. But otherwise, what is the first property that comes to your mind? Charge. Exactly. So quarks carry electric charge. They cannot be their own antiparticles, right? That's the obvious thing. What's the antiparticle of a photon? You're all sure. Yes, we've never seen an anti-photon. It can be its own antiparticle because it doesn't carry electric charge. If you say W plus, you can't say W plus is its own antiparticle. Not possible, right? What about Z naught? What is the antiparticle of Z naught? Z naught, yeah. So it's not such a huge surprise that in nature you find particles which are their own antiparticles. What about Higgs? Anybody seen an anti-Higgs? You find one, you'll get a Nobel Prize. No, it's not. You know that Higgs is its own antiparticle. No problem. So neutrinos can be either Dirac or Majorana. Now, What does all this have to do with my prior comments over here about CKM matrix? So CKM matrix here, it has three angles, mixing angles, and one phase with 3 generations. Whereas with only 2 generations, what do you have? 2 generations, which is just Kabibo. What do you have? You have only one angle, right? Only one angle. No phase, nothing. It's because of the properties of the fermion fields that you can figure out that if you do all these rotations, you will eliminate all other degrees of freedom in that particular matrix, and you'll end up with only one angle. And that's why when it comes to 2 generations, there's only one Kabibo angle, no question of 2 Kabibo angles, no question of Kabibo phase, nothing. Okay? And it's also because walks the Dirac particles. So if you had a corresponding mixing matrix for neutrinos, and what shall we call them? If there is a mixing among neutrinos, would you like to mix neutrinos? PMNS. And these are PMNS. Is it because we just like the letters of the alphabet? No, because it stands for various people. Pontecorvo, Maki, Nakagawa, and Sakata. See, even if I can't remember your names, I can remember the names of these guys. It's also a rule that there has to be one Italian and the others have to be Japanese. See? It's a good rule. So here, the PMNS with 3 generations can have 3 angles and 2 phases. If it is Majorana, like that. Okay? 2 generations, I actually don't know. Homework problem, how many angles and how many phases? Please figure it out for yourselves and then get back to me. Okay? And if I give you some homework problems, it means that you have to do them and come back and say that I haven't done it. Okay, so I want to introduce to you, because you know we all keep on talking with standard model. Everybody is satisfied with the standard model, but ultimately standard model has to do with processes, and all of us had better know what some of these processes are and what do physical observables, physical measurables actually look like, even in the simplest cases when you consider them in the standard model. Okay? And let us spend a few minutes looking at these things and trying to understand the structure of what these things look like. So let me look at Bhabha scattering. Now Bhabha is a good man because he spent time in this institute, and so it's good for us that he actually did it. So did Born. Born approximation is also good, because Born was a prof here before he went to wherever it is that he went. Okay, this is E plus E minus to E plus E minus. How many diagrams contribute to this? 2 diagrams. And I'm not going to write it down. What kind of frame should we write down the differential cross section? Differential cross section d sigma to d omega. Okay. What kind of frame should we compute this in? Center mass system. Why? In contrast to what? But in a lab it's very difficult to keep a electron at rest, no? And you can't take energy. So it's best to do it in the central mass frame. By the way, to answer one of your questions, Bhabha events are also used for calibration. I said E plus E minus to mu plus mu minus is used for various purposes, which is true, but Bhabha events are also very important to estimate backgrounds and detector performance, efficiency, all these things. Okay? So it's a very fundamental process that is useful at all linear colliders. So what is the first term that we should write here in terms of the electric charge? What power of the electric charge should the cross section go as? e power 4. I prefer to use alpha squared, and it looks like this, 2s. Because there are two diagrams, actually this thing is quite complicated, and it looks like this, s squared plus u squared divided by t squared. Can you look at this and tell me what other term there must be? And you all know what st and u are. They are the three Mandelstam variables. This guy is a genius. T squared plus s squared divided by u squared. And how did you get this? And then it turns out that there is another term that looks like this, u squared by s times t. This thing doesn't look terribly symmetric, but sorry, t squared plus, the actual symmetry is for a different one, t squared plus u squared by s squared, okay, tu squared by st. And then you have various relations like this, that u by s is minus cosine squared theta divided by 2. Now these are all things that you people should do and practice. If you don't practice these things, you can keep on watching YouTube and watching my lectures, I hope. I think this is sine squared theta by 2. I'm not sure, but let's check. Please check these things. Sine squared theta by 2. And then I actually have not written this properly. I think it's like this. So that d sigma is going to be alpha squared by 4s times 3 plus cosine squared theta divided by 1 minus cosine theta whole square. Now how do you actually do this calculation? You have to write down the Feynman diagrams, you write down the vertices, you have to write down the spinors for each one of these, then you have to take the square of the matrix element, and then there's something that you have to do, which again you keep repeating as if it's some kind of a mantra, which is that you sum over the final state spins and average over the initial state spins. And then we have relations, completeness relations, trace identities, all these things in order to get this answer. Okay? Now this is all very hard work. So instead of doing hard work, since we have now become lazy, what do? You go and look for a Mathematica program which does this. And where do you find this Mathematica program? Well, Mr. Garg here said that he's going to find it for us, but of course he was enjoying his weekend, so he didn't find it. So yesterday, you found it? Okay. So yesterday I traced it because a simple Google search didn't take me to the right page. It took me 15 to 20 minutes to find the right page. And I was very pleased to see that Romao has updated his notebooks to be compatible with the latest versions. So it is up to you people to actually download these notebooks and run them. Okay? Better than video gaming, or at least I think so. Okay. So let us contrast this with some other process, simpler process that we had already mentioned, which is e plus e minus to mu plus mu minus. And I'll do this in little more detail in a couple of minutes. At least one example we should do in some kind of a detail. Okay. So where is that? Let me look for the answer. So here it is d sigma by d omega in the ultra relativistic CMS, of course, ultra relativistic limit. And we already mentioned what this was, alpha squared by 4s times 1 plus cosine squared theta in QED. Okay. Please have a look at this formula and try to explain to me why does this formula look the way it does. Why does it have this cosine squared theta dependence like this? It has this because these are spin half particles. Okay. So because of spin half particles and the Dirac algebra, it produces this cosine squared theta. But why doesn't it produce, say, a cosine theta or a cosine cube theta and so on? Any idea why it does not produce something like that? Hmm? Correct. Okay. So whenever you have a formula, you have to think, why is it doing whatever it is doing? Since QED is a parity conserving theory, it only has this 1 plus cosine squared theta. Okay. Now you see how different these formulas look. They look like they are very, allied processes. But of course, here there is only one diagram. That's why it's so simple. While this thing here has two diagrams, and then there's a quantum mechanical interference between the two diagrams, which is why you get such a complicated formula. Here? Yeah, Haber scattering. So it depends case to case. No, even if it is there, you take this and you do a forward-backward asymmetry, you will find that it has vanished. This kind of a simple argument that I just gave about cosine theta only holds this for the S-channel annihilation diagram. Whereas here, there's an S-channel and a T-channel, and so that simple argument, heuristic argument, doesn't hold. Okay. So what is the other diagram that can in principle contribute to this E plus E minus to mu plus mu minus? So later we will add to this Z naught also, photon, and then you square this. Then you will generate other pieces which in principle can violate parity. Okay, but it's not at all obvious that it does. Okay, it can violate parity only because the Z has both vector as well as axial vector couplings. If, for instance, the Z naught was a purely axial vector, also you will not get that cosine theta term. It must have vector as well as axial vector in order to do that. So as we do this kind of examples which you can do using Romao's notebooks, he has all these examples. Please download them, each one of you, and start playing around with them. Okay. So this is of course rather nice. We could have also had a crossed process which was E mu going to E mu. Again, there's only one diagram. So if you work out the cross section for E mu going to E mu, it will look quite different. Okay, but of course you may say that, look, it's very difficult to have a muon target, so how should I do an experiment of this kind? Actually, mu can be replaced by a proton, which is perfectly okay, because you can have a proton target and you can have electrons bouncing off protons, which is basically the first process where particle physics, nuclear physics, and so on were born. And what is that process called? You people have to speak clearer. If you all mumble under your breath, obviously a person of my age can't understand or hear a word of what you people are saying. What did you say? Beta decay. Deep inelastic scattering. Well, of course, but before that there are many simple. Now, deep inelastic scattering experiments were done in the 1950s. Why? Because you needed enough energy. If you went back, people didn't have enough energy. Before that, they had to do something else. Okay, low energies. The lowest energy at which we started doing scattering more than 100 years ago. Well, first it was Rutherford, no? So Rutherford scattering is the basic thing. Rutherford is where it all started. So Rutherford is such a simple case where we behave and pretend as if the proton is infinitely massive. We don't account for its recoil or anything of the sort. And even the electron spin doesn't play any role, because the particle comes with a spin and nothing happens. It doesn't couple to the spin of the proton. It's the simplest possible thing. And there, so here, mass of the proton much greater than mass of the electron. And even the energy of the electron is small, so it is actually non-relativistic. Non-relativistic. And if it is non-relativistic, obviously you're going to get the scattering amplitude in the lab frame, right? No question of central mass frame or anything like that. And you get this E squared by 2mv squared. Because it's non-relativistic, you can speak of the velocity measured in the lab, sine squared theta by 2 squared. Soon afterwards, one made the electron relativistic. Then what do you get? D sigma by d omega mott. And this looks like this, alpha h bar divided by 2 mod p squared sine squared theta. See, you have to think about each one of these things. Why did the subject develop like this, and so on. mc whole squared plus p squared cosine squared theta by 2, like this. Please check all this. You know, I have a lot of this one, alpha h bar 2 mod p sine squared theta by 2 mc squared plus mod p squared cosine squared theta by 2. No exponential. Where? Now if actually it was exponential, it would maybe string theory or something like that, with the, you know, where the cross section is getting exponentiated. My goodness. Okay. So you can have a situation where you have an EP scattering. Also, EP scattering, and do it in the lab frame. But if the energy is very large, then you can also do it in the central mass frame. Okay. So if, let's say, ultra relativistic, you can also do it in central mass frame. See, I'm trying to convince you that there is, you know, some kind of a way in which even the simplest processes actually have to be organized in a certain way. And why is it that you go from the simplest to the next more complicated to the even more complicated, etc., etc. Now, I said here that this you can cross this E plus E minus to mu plus mu minus and call it E mu scattering, and it looks very similar to electron proton scattering. Do you think that these are exactly the same? If you calculated E mu scattering, it would be exactly the same as EP scattering or not? What do you think? Somebody even mentioned deep inelastic scattering. So you can't jump the gun, you know, and go to something very complicated without knowing the simplest ones. Okay. So what's the difference between a muon and a proton? Mass, charge. Anything else? Proton is a composite particle. So that is the basic difference between the two. So how do we do an experiment where we show that a proton is composite? Now this is of course in the standard model, and we all want to be very well educated. We want to talk about QCD, we want to talk about color, we want to talk about groups, we want to talk about quadratic Casimir. But how about starting with the simplest possible question? Why do you need all this in the first place? Experimentally, why do you need all this in the first place? Well, you people are very smart, and you told me that this delta plus plus, delta plus, omega, all that required color. Okay? That was a static property, just looking at the existence of the spectrum, and you guys said, because you are very brilliant, that there has to be a hidden quantum number that you call color. And another of you is a genius, measured the pi 0 to 2 gamma, and then you found that there's an nc squared factor sitting over there, and in order to get the correct answer, you all decided that nc has to be equal to, you missed the class, so you don't know, has to be 3. But that is still okay, it's a decay process, and it looks like a fudge factor. Fine, luckily it's also 3, just like it was with the delta. Now, in terms of really dynamical quantities, how do I know that there is a quantum number which is needed to understand dynamical properties? So far we talked about masses, and then we said that, look, this is all needed. So in order to do that, we first have to do some scattering experiments of targets which participate in the strong interactions or has constituents that have strongly interacting particles. And what better than the proton? Okay, so by now we all have agreed that the proton is made up of U and D quarks, which also carry color. But let's not go just yet into deep inelastic scattering, which you people mentioned, but let's do elastic scattering. Okay, don't jump the gun. You should do things one at a time. Do things slowly and well. That's what my parents taught me. Not that I listened to their advice, but that's the advice they gave me. Hence the advice I give you. So let's do elastic scattering. Okay. So now you people have to tell me how to generalize this. So let me write a general matrix element for this minus IE squared by Q squared. What is this Q here? It's the momentum carried by the photon. So this is a photon propagator with Q squared like this. Let me introduce various spinors for EP scattering and elastic. You people want to do deeply inelastic scattering. So first it has to be elastic, then it has to be made inelastic, finally it has to be made deeply inelastic. Each word means something, right? Now you people please help me with this. So this is for the electronic part. So what should I get after this? In QED, after the U bar, what comes? Gamma mu. Okay, gamma mu. Actually the photon should have had a G mu nu, etc., and then we should have contracted it. We will assume that it's all contracted. Then there's a U1. For the leptonic part, then what about for the hadronic part? Photons also spin half particle, U bar 4 like this, and the U2 like this. And here I'm going to do something. What should I do? Anything you want me to do here? Well, there had better be a gamma mu, and then let me multiply it in general by some function that is a function of the momentum transfer. Any other object that you know of that you can construct with the objects you have in hand, which will transform like a Lorentz vector? You have the momentum q nu, no? Which is the momentum carried by the photon. So how about that? Well, it doesn't quite appear that way, but let's add it in this way. Sigma mu nu q nu divided by 2m times f2 q squared. Okay, so this is the most general coupling that you can have for a spin half particle of this kind. If it was point-like, then this thing would just become gamma mu. Point-like means what? This two functions, f1 of q squared, f2 of q squared, are just delta functions, nothing else. Okay, that's all it means. And these have names, and what are the names that you'd like to give this? It's probing the structure of the photon, right? So these are called, no, those are all very complicated terms. This is much earlier than that. These are called form factors. Form factors, and they are functions only of one variable, which is the square of the momentum transfer. It is not a function of q nu or anything. It has to be a function of the Lorentz invariant quantity, and the only Lorentz invariant quantity you have in this setup, which is probing the structure of the proton, is the momentum that is imparted to the proton by the electron that's coming in. Square of the momentum transfer, q squared, has to be a function only of q squared. Okay. Now this thing can be rewritten, and you people have come across this in your various courses. And what is this called? Gordon identity. And what is the sigma mu nu over here? It's constructed from the These are commutators with the gamma mu and gamma nu. They are not anti-commutators. Why not? Because the anti-commutators are what define the Dirac algebra anyway, so they cannot be anti-commutators. It could have just been gamma mu, gamma nu, but since we know the anti-commutators, you can express this basis in terms of the anti-commutators, because commutators and anti-commutators together will take care of all possible bilinears. So if you already have a set of anti-commutators defining the Dirac algebra, you can just invent the remainder, which is anti-commutators, just sigma mu nu. Okay. Now this here we can evaluate in many different frames. So many different frames: center mass frame, lab frame. There's also something known as a Bright frame. You know Bright-Wigner formula, the same Bright, Gregory Bright. And you can, I have my own private notebook in order to get the cross section, which is known as the Rosenbluth formula. Rosenbluth formula. And sometimes these things, F and G, F1 and F2, they are replaced by another set called G1 and G2, various linear combinations, and these are called the electric and magnetic form factors. And you can compute these in the naive quark model in terms of the electric charges and the various Clebsch-Gordon coefficients. So you can compute in the naive quark model. It's almost like a non-interacting naive quark model. And you will see numbers like 2.78 and minus 1.91. Have you seen numbers like this? 2.78. So those are the magnetic moments of the proton and the neutron respectively, and they play a role in all kinds of things, including, for instance, the 21 centimeter hydrogen line. So the fact that these exist is a proof that the proton is actually composite. See, otherwise it's all indirect evidence, Pauli exclusion principle, anti-symmetrization, etc., etc. But the Rosenbluth formula actually is the direct way of seeing that the proton is actually composite. Yeah. They are linear combinations of F1 and F2. You will find in standard treatments of electron-proton scattering that you start out by writing F1 and F2 because it's the most easiest way of generalizing this particular vertex. But in order to really extract the information of the structure, you need other linear combinations which can then be physically related to properties of the proton and the neutron. Okay? And then it will turn out obviously that for the neutron it's going to be 0 at q squared equal to 0. Why? The electric part. Why? The neutron doesn't carry charge, right? Because so that means that the corresponding electric form factor at q squared equal to 0 for the neutron has to be equal to 0, and it will be equal to the electric charge for the proton. And these other numbers that I just mentioned, minus 9.1, minus 1.9 and 2.68, you must have come across numbers like this for the magnetic moments of the proton and the neutron respectively. And then in the naive quark model, where you have a u quark with charge plus 2 by 3 and a d quark with minus 1 by 3, you do some simple algebra, you will be able to get this. You can look at this book by Prof et al. It's very nicely done et al. You know this book, right? I sent you all a picture on WhatsApp of a stack of books. So the precise reference you can get from that picture. So let me now spend a little bit of time demonstrating. So I'm trying to ramp up the degree of complexity of each one of these processes in order to show how every single process that we have probes various properties of the standard model. You may think that this is all very trivial, very straightforward. Not really, because it is the same theory that is going to describe Baba scattering, going to describe this one. But there's one more process that I wanted to mention, which is Muller scattering. Does anybody know what this is? Now, as far as I know, Roman doesn't have Muller scattering. So I have my own private Muller scattering, which I will give you only if you're nice to me. Otherwise, I don't give it to you. How many diagrams will you have in Muller scattering? Think about it and tell me. E minus to E minus. Obviously, E minus and E minus cannot have annihilation, right? Because it violates electric charge. So they have to scatter through the exchange of a photon. So how many diagrams or a diagram should be there? 2. You're all sure? Like this, and then you can have like this, and then like this. Okay. So 2 diagrams again, and so you will immediately suspect that this is much more complicated, and it should be. And this is what Mr. Kundu here was telling us about. He tried to guess what the answer should be. Let's do this again in center of mass and say alpha squared by 2s, s squared plus u squared by t squared. Now you can guess this for me. Plus s squared plus t squared by u squared plus another term by t. So this is all manifestly symmetric under the swap of t and u. So u by s. So again, more practice. You need 1 plus cosine theta by 2, and t by s is minus of 1 minus cosine theta by 2, and this here is equal to 4 alpha squared by s, 4 by sine to the 4 theta minus 2 by sine squared theta plus 1 by 4. You see, such a simple looking process, how complicated already the differential cross section is. So if you download Roma's notebook and run all this and make all these replacements, you ought to be able to get this answer. So it is up to you to do it. Pull out his diagrams and see what is going on with each of those. Now let me stop here and let's do some participatory work. Let's have a Google Meet, not Google, Teams Meet, and one of you is going to pull out Roma's notebooks, and let's go over them so that we can educate ourselves. You can form groups of 2 or 3 if you like, otherwise instead of everybody doing things on their own. Okay, Mr. Chug, you're going to do the demo. These are all bogus excuses. What about him? Yeah. You forgot? Who has got a laptop? Anybody? Come. You don't have the notebook? We will download it. We are going to study this together. First thing you have to do is you have to set up a Teams Meet. Now I don't know how to set up things like Teams Meet and all these things. So please send an invite on the group. Let everybody log in, and then let's look at the Roma website together and educate ourselves. Okay? You're most welcome. In fact, I'll sit there and you sit here. Yeah, I'm going to sit here. Yeah. So I'm going to make you people conduct these classes. Oh, in that case, you have to take this. Yeah. See, the thing is, this S channel, P channel, thanks for you to say that way. Even Aditya had this question. It depends on whether you're doing this in configuration space or whether you're doing the momentum space representation. Okay, so I try not to think of it in configuration space with time flow here. These are momentum space diagrams. Okay.
लिंक कहाँ पे व्हाट्सएप पे कहाँ है
Exactly. What can I do about that? Come on, you have to get on the ISCW line, no?
नो नो अरे लिंक मेरे को व्हाट्सएप पे भेजोगे
So get on to your hotspot. You're right, I can't get on to W line either. No hotspot? You get on to his then. Now, these are things really, I have no words. By the way, this is the guy who wrote the group theory book, in case you guys do not. Any questions about group theory, please ask. So please get out and wait for the crowds.
रुक जा भाई हाँ हूँ मैं यहाँ पे So I'm on Teams, like how to get to the notebook. I've joined the Teams. I want to like get to the notebook now.
Now you go to WhatsApp and click on the link that I sent. So have you created a meeting for everybody or not?
Yes, sir.
Oh, really? I'm yet to see. Where?
स्क्रीन दिख रही है मेरी कुंडू स्क्रीन दिख रही है मेरी दिख रही है ठीक है अरे भाई ठीक है भाई अरे नहीं वो स्टैंडर्ड मॉडल का सर yeah so this
My best bet is to just join you. Okay.
yeah so this or this
Try both. No, that is my, anyway, let's see that also, because now that you asked.
Okay.
We started it. Let's do a quick example. I want to go through what Roma has to offer, okay? So that little by little we'll be able to go, but I have to get another chair. I don't know how to do all these things. This means connecting things and all that. Now you guys have to start participating. Will you learn all this? He wants this to be projected onto that.
Okay.
Okay, so first he's going to show us this notebook that I sent yesterday, right?
So for the notebook, I feel like I have the Mathematica downloaded, but I need the WLAN because I downloaded it from IC server. So probably I will
From
try.
what?
From IC server, I downloaded
Okay.
the thing, so I think I will just try to connect
Okay,
to
then
this.
forget it. Yeah. Then we will just go to Roma and see what happens.
Okay, I'm just trying to connect it to IC. HDMI है लेकिन एक लगा हुआ है.
Okay, so Mathematica is not working for you.
No, sir,
Yeah.
it's not.
Forget it. Then let's go to Portolis. Do you all have a screen share? You can see his screen? Okay. I understand the risks.
Yeah, it's this thing.
Yes, okay, folks, so look at this. It's a totally awesome thing. By the way, you should also look at his book. Even though it is written in Portuguese, you'll be able to follow. Okay, so let's go, because the way in which his notebooks are organized, these are companions to his book. And the book is about 600 pages. It's really fantastic. I mean, you don't really need to read the text, except some of the words, which anyway are Latin words, you'll be able to follow, hopefully. And those processes are described in the book, and then these are the companion notebooks. Okay. Now let's see here. So there are many things he does. Here it traces all that. E plus E minus 2. So you have to obviously install FindCalc also. And he has said here that he has updated it to be compatible with. Go to the top. What does he say here? Mathematica 12.1, FindCalc 9.3, and /or FindCalc 10.1. Okay. So these are the latest releases. The notebooks that I have are actually old, running on an older version of Mathematica and older version of FindCalc. But young Chaitanya here claims that he has already downloaded them, and they are working for you. And where did you find these notebooks?
On this side.
On this site?
Lost that site. So I had to give the manually to some people. So I downloaded the notebooks and then I forgot what site I downloaded it.
That's the problem. It's not easily accessible. Okay. So let's see. Let's look at some of the examples that he says. Tree-level calculations, math graph. We don't need all this. Okay. Need for Higgs boson. But see here, for instance, ITC is the name of his book. Chapter 3, 5, 6 programs. I want to know where we can find things like Baba scattering and all. So together we are going to hunt for it, okay? That's the purpose of this discussion, is together we are going to do this. That may be, but for the moment we are trying to use this guy. You see those FindCalc examples, there are only a couple, okay? Simple ones. Whereas Roma has given large number of examples. Every one of these is there. Rosenbluth, practically every single thing is there. I don't quite remember, but definitely he has E plus E minus to mu plus mu minus. He has E mu to E mu. He has just an amazing resource. Okay. If I tell you people to go and do it, I know you don't do it. That is why I'm doing it in class. Okay, let's click on programs for book ITC. Let's see what happens. Chapter 3.
Okay.
Or Chaitanya said he wants to share something. You want to share? Okay, so you make him the host and let him share. Then we can see what he has to share.
Yeah. Just
Give me the water bottle.
I've stopped sharing now. You can share.
Yeah. I think.
Yeah.
Yeah. Okay. So this is, yeah, excellent. Mu e to mu e, scattering, and let us see what is the result that he has over here. That's okay. I want you to look at what is the result and what do we get over here, okay? So he has a notebook, mu e, is it? So let's have a look at that notebook. Do you have it? Open that notebook, let's see what he has there. How do we see what are the lines over there in mu e, mu e? Yeah. Here. See here he says that this is the definition of the program. So why don't you explain to us line by line what is done, okay? Move your mouse and explain what is in what. Yeah. Not him. He has to move the mouse.
I was just removing.
First case, find the property here.
Yeah.
I don't understand what is GS of T is. I think it's just 1 by T square minus.
No. GS is gamma slash. GS is gamma slash. Okay. Okay. So these are the commands that you need to know. GS is gamma slash as far as I know. You have to look into the FineCalc manual to know what each of these commands is. Okay. So let's have a look at FineCalc page since it's going to be a tutorial today. Just open the FineCalc manual. Yeah. You Google FineCalc, then you look for manual, and then you click it. Yeah, FineCalc manual. Yeah. Hmm? Next time, next class. We don't want to waste, but this is also a nice way of doing it. Now listen, we have gone through COVID, okay, where we have not even seen each other. But this is a useful skill that we have learned from COVID is to be able to do these things. We have to be infinitely adaptable. Okay, so our friend here has got okay, guide to find calc. Why is he given this hand? So you look GS. You do a search for what is GS. Okay. There you are. All the commands are listed over here. Basic objects. Yeah, let's scroll down a bit and together we will read and see what is going on over here. Okay, let's go back to the notebook and let's see what's going on. Or you first look at that manual to see what GS stands for. Do a search for GS.
Yeah, just Control F
Yeah.
GS. Yeah.
You will have 8,000 hits for GS. Just look for gamma slash. I think that's what it stands for now. I'm not sure. I again forgotten everything. Okay, let's go back to the notebook and let's see what it does. Now you all know that you have to get involved, okay? Start downloading these things and start following them. Okay, let's go back to the notebook and see what he does. Gamma slash P plus M. So you have these propagators. Okay, so it's obvious, right? Line 1, he says propagator with momentum P4 with mass M2. Then dot Ga mu is what? Gamma mu. Okay. Then prop P2 comma M2. So he has one line here, another line here, and then he has these vertices between the two of them. Okay. So that's line 2, and then he uses these internal commands of contracting. I don't know what TR is. TR is probably trace. Must be Dirac trace. Okay. Yeah. Then answer is just this. So if you run it, then this gives you the amplitude. So these here are telling you how to do the Dirac algebra. That's all, very straightforward. Okay, good. So this is one simplest possible example. And if you run it, what did we get? He ran it in the other notebook. This is the input where the particular process, this is input into the other notebook. Let's go to the other notebook now. So when you go to this notebook, you can see clearly very good, but it didn't give the answer that we wanted. Okay, doesn't matter, but at least Chaitanya has taken the effort to download these things and to start. Some of it means what?
Some of the abbreviations are off. The printing is off. There is some answer.
No, but it has not done the answer. You see, it has still kept it as trace and all that. I think you have not run fine calc. That's the problem.
Yes, of course.
You have to, yes. Please kill the kernel and do it again. Kill the kernel. Okay, let's load fine calc. Very good. What's taking so long? Okay, good. Now you load the notebook. Let's see what happens. Okay, but we don't. You have to scroll. We can't see it. Scroll down. Ah, yeah. So this is the result after running it. See, so finally, as you can see, this is 1/4 of the sum over spins of mi squared is an answer that involves only the kinematic quantities. What are the kinematic quantities you have in hand? The four momenta,
Mass and
four momenta, P1, P2, P3, P4, and the masses, which in this case are just M1 and M2. So after doing all the spin sums, you're going to get this. Why 1/4? What is the 2 into 2 that you are doing? So let me ask you a question. Why do you average over the initial spins and sum over the final spins? I mean, we all keep saying this, right? Why? Correct. Why?
Because when we measure the final state, the spin gets measured.
Good. Excellent. So you people know everything. Okay, let's go to the next notebook and see what is going on. And let's look at the menu, what it is that he or he has to offer. Is it a buffet or it is a la carte? You can decide. Okay. Some of you may like buffet and you want to have a little bit of each. Some of you may be very eclectic and you want to say, I only want to do Compton scattering and nothing else. You can do that. Others may have even more refined taste and say, I want to do Compton scattering, but I also want to measure the final state spins. Luckily, Romao on his menu card offers us all these possibilities. It's really incredible how many things he has. Okay, let's open another notebook and see what is going on. Yeah, let's have a look at that. Then we don't want to do something that complicated. Okay. Now you people can do all these complicated things after you're done with this course. When we are doing this course, let's at least each of us do a couple of simple examples and learn some basics, okay? And learn how to do these things using Mathematica. Now what is this? I suppose I should have been wearing this, doesn't matter. But still, I hope the recording.
Yeah, the voice is coming.
Okay, so. S stands for the spin vector. Okay, so whenever he says GS, he is doing a gamma slash of the vector that is given as the argument. Okay, so if it is GS of P, it means gamma mu P mu. If it is GS of small s, it means gamma mu S mu, where S mu is the spin vector. Okay, so it is S slash. So if you introduce S slash, it means that you can look at the polarization of that particular Dirac particle. Okay. So that is why it's GS of S, where S is the spin of that particular particle. So good. You see here, if you look at these notebooks, all these very, very tough calculations that you see in books will become readily accessible. Now, why don't you download this book and let's have a look at it also to see what you people can learn on hand. All these books are more or less the same, whether it is Renton's book or Griffith's book or the other books that I use, Florian Check, all excellent books. But Romao he has obviously tailored his notebooks to his book. Okay? So let's download his book and have a look. And that this is the most efficient way of learning the stuff. And tomorrow when you people become teachers, you can use his book also. Book. I don't think it's published. He just has, he has a PDF on his website. Yeah. Yeah, you can share it. Excellent. See,
Unshare your screen. Yeah, I have this book open.
Yeah, just open one of the chapters. Let's see what it looks
Let
like.
me just see whether, yeah, advanced.
How come you have so much security?
I just, yeah, these are the files.
These are the files. But let's look at the chapter itself. I don't want to look at the notebooks. I want to see the chapters in the book.
Okay.
No, but this is very nice. You see
Yeah.
here, he is showing everything here. E minus, mu minus to in QED.
Mhm.
Hey guys, talk later. Here.
So-
Follow what is going on over here. Polarization, Coulomb scattering. These are all the notebooks, and this is where you can get them from. But let's look at the notebook, at the chapter itself. Let's see what he describes in the chapter.
So,
So you have to go to the book, previous.
previous.
Go to the book. Oh, he's saying up.
Okay, let me just.
Yeah, go up. We need to go to the book. Do one more up.
There is no more.
There is no up. Okay,
Yeah.
so you just Google over there Romao, his book.
Book on.
Field theory.
On.
Yes, say Lisbon also. Say Lisbon. Jorge Romao. Unless you say Jorge, you will not get it.
Lisbon. Okay.
Lisbao. B-A-O.
Yeah, this one.
Yeah.
Mm.
Yes. Okay. You see, oh, he now has an English version. Good, good.
Okay. So what
And
should
at
I
least,
search?
At least the table of contents. Nothing to search. I want you to get familiar with it. Okay. So let's look at some of the chapters, some of the pages, and see what he says.
Mm-hmm.
Okay. Look for some processors. You know? We don't need all this basic stuff. Just go to page 200. Let's see what happens. 200 is not good enough.
Yeah.
Let's see.
Prob-
300. Yeah.
Okay. That's appendix.
It's too far.
Electron,
Okay,
positron.
see here. And it's amazing, it's now in English.
Yeah.
So you guys are lucky. I had to read the Portuguese version. Okay, so does he say where the calculation is? Here.
Yeah.
Yeah.
The diagrams.
So everything is here. You people can follow this and then you can calculate.
Feynman rules and. Does this also have, like, is this just a book about theory or does it also have mathematical things?
I think those notebooks are companions to this.
Okay.
Aren't they? Am I right? Yeah.
So this is.
QED renormalization at one loop, which is all very good because these diagrams, if you want to sit down and calculate, each of them will take you an hour to do. His notebook, you can do it in 10 seconds, okay? Of course, assuming that you already appreciate the science. Okay, so keep going. So we will take a 10-minute break and then we will reconvene because I'm teaching the Sudhir's hour today, as I told you. Okay? 10-minute break is good. Then we'll get back to Blackboard teaching. But this, I wanted to do this. Now you can't say that you were not actually introduced to this. Okay, we've done an online, on hands. So in future, hey guys, wait. In future, in some of the, hey, take it easy. In future, some of you will actually have to give a demo. Okay, you will have to go to the Blackboard. You have to draw the diagrams, and then you give a demo of this using these notebooks and say what is what, explain the formula, explain what is the cross section, take various limits. You can use this as a backbone and you can plot various things, you can plot distributions, use the formula to show what the cross section looks like. Don't just be satisfied that you have a formula. Plot it and see what it looks like. For instance, he has Compton. Compton is a very complicated formula, and unless you actually plot the Compton cross section and so on, you will not be able to really appreciate it. There is this Klein-Nishina formula also, which is a limit of Compton scattering. It's very complicated, but this guy has given it. Is there Klein-Nishina? See in his notebook, in his book. Control F.
Yeah.
Klein, K-L-E-I-N.
Klein?
Klein is enough. Just hit it at a time. Klein-Nishina. Okay, look for Nishina.
Klein-Gordon.
Look for Nishina.
Yeah.
Nishina.
There is no.
Okay. No, look for Nishina.
Nishina. What's the spelling?
N-I-S-H-I-N-A.
Nishina. Nishina. No,
Okay,
there is
fine.
no Nishina.
Okay, good. So then we can use his Compton and then we can take limits and show the Klein-Nishina formula. Okay? By all means. Yeah. Okay, good. So we take a little break and then
So do we need to stop the...
no, let it be. I'm going to do all this much work. Now these formulas, if you run Romao's notebooks, you will actually be able to get all these formulas. Okay? Now he may have stopped over here. Then you have to do a little bit of work by introducing them. Okay. So after Rosenbluth comes the deep inelastic scattering, which of course I'm not sure we should really do over here. Presumably you've done it in some of your classes and you already know, or should I do a little bit of deep inelastic scattering later, not necessarily now? Deep? Okay. Okay, so the main difference is that up until elastic, we have just d sigma by d omega, okay, because of energy momentum conservation. But if you have inelasticity, then you have a second derivative d squared sigma by d omega d e prime, because then you have a lot of energy absorbed by the target. And so in deep inelastic scattering or any other kind of inelastic scattering, you will see a doubly differential cross section of this kind, which is something that we will do later. It's a more advanced kind of topic. I'm teaching Sudhir's class today, but you're welcome to be here, of course. Yeah. Imbibe some standard model. This is standard model, while that is beyond the standard model. Okay, so now I'm going to discuss for you from Renton. Doesn't matter, all the books are the same, E plus E minus, to FF bar, where FF bar is not the electron. We have these two diagrams, photon plus the Z naught, like this. So here, the matrix element will have a contribution from the photon, have a contribution from the Z, and this is what it will look like. I E squared by S. Now we explicitly write Q E Q F. The reason we do this is because later you may want F to be, say, a U quark or a D quark or an S quark. Okay, so we keep the electric charge here like this. Then you have a V2 bar, gamma mu. Now different books have different conventions, but we'll get used to it. U bar 3, gamma mu, V4 plus, let's see what this looks like. I G squared by cosine squared theta W times S minus mz squared. In principle, this should also have an I gamma Z, but it's small, so we can put it equal to 0. What is this I gamma Z that you have to put over here? I gamma Z mz, of course. This is the width of the Z. Okay, in principle, it should be there. Then we have a V bar 2 gamma mu. And now comes the tricky part. The tricky part is the introduction of the couplings of the Z naught, which are different from that of the photon. Okay. So standard model. We keep talking standard model. How many standard model parameters do you already see over here? E is the electric charge. Obviously, it's a standard model. Parameter G here. It's a weak coupling constant, which is associated with the W boson. Okay. So the additional cosine squared theta that you are seeing over here, theta W, W for Weinberg, cosine squared theta W, is because this is the coupling of the Z. Okay. If G is the coupling constant of SU2, SU2 cross U1, there's a G and then there's a G prime, and then this breaks into U1 electromagnetism, which has its own electric charge. It's the G over here, whereas the part of the standard model gauge group that remains unbroken because of the Higgs mechanism is electromagnetism. But in this breaking, you get W plus, W minus, and you get a Z naught. You get an MW and you get an MZ. And a particular combination of G and G prime is E, and the orthogonal combination of G and G prime is the coupling of Z. Okay? That's where the Weinberg angle comes from. One particular linear combination is the electric charge. The orthogonal combination is the coupling of the Z. Okay? So all this we will do in a little more detail later, but you have to observe that in any process that we discuss, various standard and model inputs are coming in. Okay? So this is again the standard model. Yeah. S minus mz squared plus I gamma z mz, where this is the width of the Z times the mass of Z. Normally we neglect it because it's numerically small compared to the mass of the Z, so it's discarded. Okay, so after this gamma mu, what do you think I should write over here? Because it's a V minus A theory. V minus A theory. So what should we write? Huh? Good guess, but the wrong guess. 1 minus gamma 5 is for the W. Okay? So here it is a vector part and an axial vector part. So that is G EV GEV minus GAE times gamma 5 times U1 times U bar 3 gamma mu. And what shall I write over here? What should we write over here? Obviously a vector and an axial vector, but this time for, look at the reaction, FF bar. So what should we have over here? GVF minus GAF gamma 5 times a U4, like that. I think it's a V, sorry. What? Yes, okay, fine. Where GV, the vector coupling is CL plus CR, GA is CL minus CR. So the standard model tells you exactly what the CL and CR are for each one of these. Okay? The standard model gives you in terms of the quantum numbers under SU2 cross U1. Okay? Exactly how these transform as representations of SU2 and U1. So M squared is M gamma squared plus mz squared plus m gamma mz star plus m gamma star mz, as it should be. And let's see what it looks like. D sigma by d omega of course, center of mass frame is alpha squared by s. You can reabsorb these things into the alpha squared times C1 plus 1 plus cosine squared theta plus finally, and this was Ranjani's question about the cosine theta, that's what shows up over here. And this is the parity violating piece. And the C1 and C2 and so on are expressible in terms of these charges, GAE, etc., etc. But it is good for the soul to write it at least once. C1 is QE squared, QF squared. Please observe the structure, okay, of each one of these things. F squared by 16, GEV squared plus G E axial vector part squared times E goes to F plus F by 2 QE QF GVE GAE. By the way, Romao also, as far as I remember, gives this process with inclusion of the Z also. I'm sure he has a notebook somewhere where he has a full electroweak thing. So you can plug it in and have a look. C2 is F squared by 2 GEV GEA. Now observe the structure. Everything comes in rather symmetrically. GEFA plus F times QE QF GAE GAF. C2 cosine theta, yeah, okay. So you see, you need to have both vector and axial vector type couplings in order to have CP violation. Okay? The P violation. This is not something that is easily appreciated. People think that if you have an axial vector like coupling in a theory that you'll immediately have parity violation. No. It has to come from the interference of both types of couplings. There's no other way. Any other missing terms? Yes, here. F squared is G squared by E squared cosine squared theta W is times S by S minus mz squared. Now I'm going to write this again in a different way just to show you that there are so many different relations among standard model parameters. I already said that this E and the G prime are already related, okay? And then this cosine theta is actually the ratio of that G and G prime, or sine theta, I don't remember quite. I think tangent is G by G prime of tangent of cosine theta W. So this G and E can be eliminated and written as sine squared theta W. Cosine squared theta. So these are all relations that you have to know. If you claim that you know the standard model, you have to know all these relations, mz squared. These are all cross checks on the consistency of the standard model. So you see, you can get rid of this G squared and E squared and replace it by sine squared theta W. So what exactly are the vector and axial vector couplings of various standard model particles? So I'm going to ask you, because you people have done some courses on particle physics. So let's name a particle. Let's ask what is its vector coupling and what is its axial vector coupling. And what are the particles that couple to the Z? Now somebody tell me, what are the possible FF bar pairs associated with the Z naught? What can it go into? Photon. What are the FF bar that this can go into? Okay, then? Okay, So I'll keep it as electron type. So mu1 tau, I don't want to repeat. Then UU bar, then DD bar. Anything else? Hmm? Yeah, that's true. But I'm talking about fermions. The process we are looking at is the FF bar. What about this? What can the Z0 couple to? Hmm? Neutrinos also. E plus, E minus, UU bar, DD bar, DD bar, and neutrinos also. So, let me see here. Neutrino type, electron, U type, D type. So GV here is, so remember, it's L plus R, right? So neutrinos only couple to L. There's no R. So GV and GA are equal for the neutrino because there's no R. It doesn't couple to the right-handed. So half and half. And for the electron, it is minus half. Why minus half? Because the neutrino and the electron form an SU2 doublet, okay? So it is plus half and minus half, okay? Because it's the doublet. But because it's mixing with a photon, it will get a contribution also from the electric charge, and this is plus 2 sine squared theta W. And this is a minus half, because the weak part of it, the SU2 part of it, couples only to left-handed fermions, okay? That is why you get only a minus half for this. Now please tell me here, let's start to guess what these things are. What do you think it should be? Here, 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 here. Look at the structure and tell me what do you think we should get over here. It'll be like this part will be the same, okay? So let's get a half, minus half, half, minus half. But there's a contribution that's going to come from here, which is from the G prime part. So that gives the sine squared theta W. But in addition, there's something that involves the electric charge, okay? So here if it is plus 2, what do you expect to see over here? Minus 4 by 3 sine squared theta W. It is minus 2 times the electric charge of that particular particle, and therefore here it should be plus 2 by 3 sine squared theta W. So now I'm going to give you an exercise, and I'm going to ask you to compute the total width of the Z0 and the branching ratios into each one of these pairs. So here it is. So the partial width into an FF bar pair of a Z0 is gamma naught times, oh now it is given as G hat L of F squared is G hat R of F. See, different books like to use different symbols. Where G hat L is 1/2 of GV plus GA, G hat R is 1/2 of GV minus GA. Okay, and gamma naught is something that obviously has to involve the Fermi constant GF divided by, I think, 3 pi square root of 2 h bar c cubed mz to the 6 c to the 6. Okay, now you people can take out your Mathematica notebooks and compute these widths for each of them, for each of these. Okay. You can take out your computer, calculator, Mathematica, whatever, and compute this for me. One of you has to volunteer, come and write down the values of all these various constants, and GF, anybody? GF equal to? By now you should have it in your head. Yeah, but okay. What is it? 1 point? Minus 5 GeV to the minus 2. Okay, then NZ 90 1.187 GeV. So gamma naught you can calculate and let me know what it is. Now we can just express it in GeV, then we don't have to put H bar C, all these things, okay? Because this GeV to the minus, no, maybe we need it, 6, 2, wait a minute, there's something wrong here. This doesn't quite work. Oh, H bar C cubed, so that is MeV femtometer cubed, yeah. So we'll have to plug in all these things and see what this number is. Okay, you have to do it. Put it in Mathematica and get it for me. I remember doing it in Mathematica. Okay, doesn't matter. I'll tell you the answer. It's 0.633 GeV. So the width also obviously has to be in units of GeV. Okay, that is one thing to keep in mind. And if you plug in these numbers, you will get gamma nu is equal to 166 MeV, gamma E, gamma mu, gamma tau are all about 83 MeV. Gamma D, what else should I have? Gamma D, gamma, anything else? What is the other D-type quark? D-type quark? DSB. And each of these is approximately 122 MeV. And then gamma U, and then gamma C, then T. Really? Sure? What's the mass of the top quark? (175 MeV). Okay, so mass of two top quarks is 175 times 2 is how much? 350 MeV. And what's the mass of the Z? 90 MeV, 90 GeV. I am talking about 175 GeV. Okay, top quark is 175 GeV. It's as heavy as, say, a mercury nucleus. Okay, something like that. Some incredibly heavy nucleus. So two top quarks is 350 GeV. So obviously the Z cannot decay into TT bar, no? Impossible. So only this, and this is 95 MeV. So please calculate the total width of the Z from this formula and tell me what you get. 166 plus 3 times 83, 249, plus 366 plus 190, Somebody add this up and tell me what this is. (971). And what's the width of the Z according to particle data book? Yeah. You're right. I think it's times 3. I think maybe I think I added up all 3. I have to check with the book. Okay. But there's still a trick part of this which I have yet to get to. Yeah. Why don't you just quickly check this for me to see what is the answer? But no, it takes too much time. So what's the width of the Z? PGG is not opening. I swear. So we are not getting the right answer with just this. Okay? Exactly. So that's the trick part. So here is a direct proof that these things have to be multiplied by 3. Okay? So again, this is again experimental proof that the number of colors has to be equal to 3. Okay. So when you say standard model and keep screaming about standard model, it means that every one of these things you have to account for. And standard model is not just electromagnetism, it's not just weak interactions, it's not just electroweak, it is electroweak and strong interactions always together, because most of the time it's impossible to disentangle the standard model, the strong part of the standard model. And the big difference between the strong part and the other sectors of the standard model is that the particles, the quarks and the gluons are confined. And it's very difficult to do any perturbative calculation with these things. However, in an experiment like this, where you let's say produce Z, this U and U bar quarks may be produced, but then it hadronizes and produces some bound state of UU bars. And if you have an inclusive cross section, your detector is going to receive all particles. Okay? So it's only the inclusive cross section that you can actually measure, because the detector cannot really see them as quarks, but it sees them as pions, kaons, and other particles of the sort, or B mesons or Chum mesons. It will not see them separately as quarks. Nevertheless, when it comes to calculating branching ratios of this kind, you can still do it because it's an inclusive measurement, and therefore it's not necessary for you to be having any exclusive information as to what the final state was, okay? Because your detector is going to sum over all the particles. So this is another very important piece of evidence that the number of quarks is actually equal to 3. And this is coming from a dynamical process of this kind, like a Z0, which then decays, and then you sum over the cross sections. And note that in the couplings of the Z0, you don't have CKM matrix elements, nothing, okay? Because it is flavor diagonal, and therefore there is no quark mixing features that come in over here. Similarly, you don't have to worry about nu bar and all these things, okay? There's no mixing involved in this particular sector. So in the small exercise, you have already seen many features of the standard model. You have seen the fact that there is chirality of this kind, which distinguishes between left and right particles. There's no contribution coming from any right-handed particle. That's why the GV and GA are equal for the neutrinos, and the GV and GA are equal up to contributions involving sine squared theta W, and that's because of the mixing. And yeah, so this is what it is. And these are all things that you should know about lifetimes, branching ratios, things of this sort. Leo was asking me about what are the explicit homework problems. I haven't actually written them down, but what I say in the class is essentially your homework. to go back, check these numbers, put them into the computer, put them in Mathematica. Make a mental note of each one of these things. Because again, tomorrow, if you're asked, what do you mean by standard model? You have to be able to say that these are all the features of the standard model. Here, you see this particular relation here for sine squared theta in terms of these guys is actually a very important keystone of the standard model. So let me pause over here and ask you to evaluate the ratio of the W mass squared to the Z mass squared. Now that I mentioned sine squared theta W, I want you to evaluate for me using your calculator mw squared by mz squared. Plug in some numbers. 80 point, what is it? 377 divided by 90 point, 91 point. I think we just had 187. And square it. Please give me a number for this. Point 0.777. Please give me 1 minus 0.777. Point 2. Yeah, it's a bit small. I prefer a somewhat larger number. Are you sure it's 80.377? Sine squared theta W. 0.369. Okay, and this is? Okay, so it's 0.77. Okay, so 0.2. This is 0.234776. Please check the value of sine squared theta W according to particle data book or whatever. Particle data book. What does it give? Yeah. Yeah, so there's a bit of a mismatch over here, but this is the basic relation that mw squared by mz squared is cosine squared theta w. Okay, so you must know this relation also. So then, what's the other relation that we looked at? G squared by E squared is 1 by sine squared theta w, right? Now G, I think, is 0.651. So somebody get G squared by 4 pi for me. Hmm? 0.0337. So let's look at the reciprocal of this. Sine squared theta w is alpha by alpha w, let me call it 1 by 137 times 0.0337. Let's see what this is. So it's not all hanging together, so we have to be a bit, oh, I know why. Because this is not 1 by 137, but we have to evolve it to near the z, it's 1 by 128. Okay, let's do this. See, this 1 by 137 is a value of alpha in the Thompson limit, okay? So we have to compare these things at the same scale, and it changes to 1 by 128 by the time you get to z0, as far as I know. What does it give? Ah, thank you. You are my pal. So this is to force you all to think about these numbers. Of course, you'll hate me for it, but what do I care? I don't know. We have to look into it. Okay. So exactly what is the definition, masters? It's yeah. So we have to check. I don't immediately know why, but this is one of the definitions of. So you see, again, when we say standard model, everything is confirmed, this, that. Even a simple example, we have already run into things where we need to do more work to figure out exactly what we are comparing with what. Okay. Exactly what is the definition, we have to look. Okay. It's possible, yes. Yes, Leo's thesis advisor or teacher, Hans Gardner, he's the guy who's the world authority on all these things. So you ask him. You can send him an email to ask. Because if we wrote, he may not reply. So maybe if you write, he may reply. Okay. Now, let me think of one more almost pure weak process. And what is a really pure weak process that we can have? A muon decaying into a neutrino like this, and then electron and mu E bar like this. Okay. So let's name these things P1, P3, P2, P4 like this. How about helping me introduce the matrix element for this? GW squared by 8 MWC squared. Now all this is fine, but what about the Fermi constant? What is the connection between the Fermi constant and G and MW? GF by root 2 is equal to GW squared divided by 8 MW squared. Okay. Can somebody get me GW from here, from this particular relation? Okay, let's do it. 1.16 times 10 to the minus 5 divided by square root of 2 times 8 times 80.37 squared, and then please take the square root and tell me what this is. So if tomorrow somebody wakes you up in the middle of the night and asks you what on earth are standard model parameters, you at least have to be able to rattle off some of these relations. Okay. Now, what's the answer? Yeah, 0. Thank you. She's my friend, I tell you. 0.651. Okay. Now you all had better memorize all these relations. This is a relation that you have to memorize if somebody asks you standard model. This is another relation. These are all relations that you should know. Okay. And here, this is another relation. This is the same, of course, as this. And this is the fundamental relation where the Fermi theory is the effective low energy theory of the weak interactions. So it's a 6 dimension 6 operator for Fermi interaction, as it is called, and this is what it looks like. Okay. So GF by square root of 2. I don't know why he did that. U bar of 3. Now you tell me, what should my vertex look like here? What should my vertex look like? Here's my friend, one of my friends here. He was telling me 1 minus gamma 5, right? Who was it? You did. What would you like here? Here it's 1 minus gamma 5 because these are neutrinos and they have no other thing. There's nothing else happening. So it's 1 minus gamma 5, and then U1. And how about here? U bar 4, gamma mu, 1 minus gamma 5, V of 2. Yeah.
I probably missed what is the input and input for the electron. Instead of 1 minus gamma 5, you wrote mu minus gamma 5.
Yes, yes. That is for the Z couplings. This is for the W couplings. Here it's W, no? So W is in the SU2 part only. So here the coupling is 1 minus gamma phi. The Z is a mixture of W3 and the B meson of the U1. Okay? So SU2 cross U1, let's call it B. The generators here are W plus minus and W3. So one particular combination of W3 and B is Z. The orthogonal combination is the photon. So this has a coupling constant G, this has a coupling constant G prime. And then this is broken into U1 electromagnetism. You must have seen this in your particle physics courses, right? So here the coupling constant is E, and E is related to G and G prime. And the Z, which is the orthogonal combination, Z is orthogonal to photon. Its coupling is also related to G and G prime through these factors. Okay? Whereas the W plus W minus is sitting only in SU2, so the only coupling constant is G, or what I've called GW over here. Okay? So the matrix element has a very simple structure, and please do this using Roma or using fine calc and prove to yourself that this coupling constant is indeed very simple to GW by MW squared, I think G to the fourth, I suppose, MW squared, so it must be to the fourth power. Check here, P1 dot P2, P3 dot P4. Such a beautiful structure, okay? And finally, what do we have to do after getting the square of the matrix element? What is the actual observable when the muon decays? It's the lifetime of the muon, okay? No, there's no tau. Oh, you mean the lifetime, tau, which is 1 by gamma, which is the width. So in order to do that, you use the Fermi golden rule, square the matrix element, then find out all the allowed phase space, do the phase space integral, which is of course very complicated, and we are not going to do it. We just write down the answer for the lifetime. Okay? But by now, all of you young people know, which I never knew, is that now neutrinos mix. So what about the PMNS matrix elements here and the PMNS matrix elements over here? Think a bit and tell me why is it that I have not included those coupling constants. In the year 2025, you would imagine that you should introduce all these mixing matrix elements. No. The PMNS matrix element should be present at the vertex, right? But it's not. Because you're going to have an inclusive measurement. The only particle that is seen in the final state is the electron. The neutrino and antineutrino disappear. So you don't know for sure whether it was a mu type neutrino or an E type neutrino, or actually a mu prime, E prime and a tau prime, because you can introduce a PMNS mixing among the neutrinos. There'll be a matrix element at each one of these vertices. And when you square the matrix element, you get a square of each of these matrices. But because it's inclusive, you sum over all of them, and because the matrices are unitary, you get 1. And it disappears from the matrix element because it's just equal to 1. So the old calculation that we did without PMNS mixing is allowed because it is inclusive, okay? Because all you see is the electron in the final state. So you don't care whether this was a mu prime or an E prime, whether this was a mu prime or an E prime or a tau prime. Here also whether it is an E prime, mu prime, tau prime, because you're going to sum over all the final states, okay? If there is a violation of the unitarity of the PMNS matrix, then obviously this will be corrected by some very small correction, but it's very tightly constrained. And the only way it may be violated is if there are sterile neutrinos or some other particles participating or some other contribution from unknown BSM physics, then you may get a further correction to this. But if it is just normal massive neutrinos, which are just mixing, and because they are not observed, you don't see anything in this particular rate. Okay. No, this is all momentum space. There's no time over here. That's what I was trying to say earlier. Okay. These are Feynman diagrams, momentum space representation. And please don't take me seriously with particle, antiparticle, arrow, no arrow. This is all for your homework problem to get it all right. I'm so old, doesn't matter to me anymore. But for you, it'll matter. So, after squaring and so on, then we will get the lifetime, which you call tau. And I want you to look at this, 192 pi cubed h bar to the 7 gf squared mu to the 5th power c to the 4th. And I want you to compute this and get the lifetime. Okay. Okay. Now somebody plug in all these numbers and then get the lifetime over here. Now everything is in GeV units, right? So this width will be in GeV. So if you look at the width, then you don't have to do, you can just forget about h bar and you can forget about this. So you will get the width, and then you have to take the reciprocal of the width and multiply it by the value of h bar in MeV second units. Okay. So please look for value of h bar in MeV second. Can somebody tell me what is h bar in MeV second? Look at table of physical constants in PDG. Just Google PDG table of physical constants. -6 minus 22 MeV second. So then this reciprocal of this, you had better compute it in MeV. But let's first do it in GeV and then let's see what happens. So GF 1.16 times 10 to the minus 5 squared times 0.105 to the 5th power divided by 192 pi cubed. Yes, that's all I need. Please, somebody get me this number. Then we will take the reciprocal of this. So this is gamma in GeV. What have I done? The spins and all those things. Yeah. Thanks. This is the average of the spins. What did you get? 2.88 times minus 19 GeV. Very good. So let's now take the reciprocal of this and multiply it. So this is 6.58 times 10 to the minus 25, right? GeV second. So take the reciprocal of this and then multiply it by that, and then you tell me what is the answer. .58 divided by 2.88 times 10 to the minus 6 seconds, and this is that good or is that bad? 2.2 times 10 to the minus 6 second. So you see, this is a formula which is telling you that the lifetime of a muon is 2 times a millisecond. This is extremely important for all particle physics or cosmic ray physics or anything. Why the muon is so long-lived? Why is it so long-lived? Because there's nothing else for it to decay into. Okay, it can only decay weakly, unlike many other particles which can decay. So it's a weak decay, and this is a typical example of a weak lifetime, where the muon is so massive that all its daughters are massless. Okay, so in a sense, it has a maximum possible phase space to decay into. Okay. So can you think of one more example that we could do where we may think of this kind of a decay? Let's think of one more decay, because nature has been so kind and has provided us a copy of the muon. And what is that copy of the muon? Tau. Very good. So what can the tau decay into? Tau can definitely decay like this into an electron and 2 neutrinos for sure. No problem. What else can it decay into? Muon into 2. And what else can it decay into? It can decay this W over here that is produced, that gives you an electron and an antineutrino, may just as well have been a U and a D bar. No problem, right? W couples to a U and D bar. So it can go to a U and D bar. Anything else it can decay into? Now think. Now U and D bar is produced, and then it hadronizes and produces a pion, 2 pions, several pions. Doesn't matter. At the level of the quark diagram, it is a UD bar W vertex. Okay? And then there's a further hadronization, and then the quarks, they hadronize, they produce, gluons and all these things, and then they get bound, or if it has a lot. Since the tau is very heavy, it can produce all kinds of particles in the final state. Anything that is kinematically allowed, there's a probability for that. 1 pion, 2 pions, 3 pions. It can produce for the simple reason that mesons do not carry any baryon number. So there is no conservation law that is violated when you produce 1 pion, 2 pions, 3 pions, etc. Okay? It can also... Yeah, sure. Yeah, tell me. Thank you. Okay, one of them is antineutrino. Fine. Is okay? Then? C, are you sure? Yes, but what is the lightest charm system? The mass parameter of the charm quark, you're right, is lower than this, but the lightest charm mesons, the D meson, is actually heavier than this. It's kinematically not allowed. Okay. You're right, they are very close to each other. You don't get. Okay. So now you people are going to use this formula that we had, and you're going to compute for me the lifetime of the tau. As usual, trick question. So please get the tau lifetime properly for me. So let's look at this formula here, okay? Or this formula here. The only dependence of the mass is this 5th power of the muon mass, okay? So for the tau lepton, this would be replaced by the 5th power of the tau, okay? So you immediately know the scaling relation. It has to be m tau divided by m mu to the 5th power, okay? And how many such final states are available? Wrong, because the quarks come in 3 colors, okay? Probably. Now in mathematics and physics, At least in the world in which we are level, nothing is probable. Everything is deterministic, at least in systems like this. Okay? So 3 colors. However, there is the Kabibot-Chugh angle over here. This is the cosine theta c, and this is the sine theta c. So in the rate, sine squared theta plus cosine squared theta gives you 1. So 1 plus 1 plus 3. Okay? So you can't add lifetimes. You cannot add lifetimes. What can you add? You can add the widths. Okay? So you have to take the width, you have to multiply it by 5 and scale it by the 5th power of the ratios of the masses. Now you tell me the lifetime. U bar and electron. You cannot, because you violate electron number conservation. Because of the coupling of the W to the U, and D bar will have the cosine of theta c. Okay? If this was the S bar, so D bar S bar would be sine theta c. In the matrix element, in the square of the matrix element, sine square plus cosine square. Okay? Of course, we are pretending that the 3rd generation doesn't really count, approximately. These are much larger than the other mixing angles, so for this purpose. So what's the lifetime? What did you get for the width? So gamma tau is gamma mu times 5 times m tau by m mu to the 5th power. Okay, so let's find out what this factor is. So 5 times 1.78 divided by 0.105 to the 5th power. Let's figure out how much this is. So I would say that this is roughly 20 to the 5th power times 5. What is 20 to the 5th power? 2 to the power of 5 is 32. 32 times 10 to the 5 times 5 is roughly 160 times 10 to the 5 is roughly 1.6 times 10 to the 7. That's my guess. But what is yours? So the lifetime is down, divided, where is this? Divided by this particular number. So it is what it is. Is that what you get? Hmm? So my estimate is wrong. Okay. So this is 7 into 10 to the power of 6. So tell me, what is the tau lifetime now? Is 2.2 times 10 to the minus 6 divided by 7 times 10 to the 6, right? Approximately 3 times 10 to the minus 13 seconds. You see, it's so many orders of magnitude down in terms of its lifetime. Okay, I think I'll not be able to. I think this is enough. Everybody is saturated. Certainly I am. You want more? पूरा पैसा वसूल करना है? नहीं. Yeah. No. That's from here. The 5th power is coming from here. Yeah. And the 5 is coming from 3 times the quarks, because of the 3 colors. 1 for the neutrino, 1 for the electron type, 1 for the muon type. No, it's an inclusive measurement. Remember that your detector is just going to see hadrons. Okay? Yeah. Yeah. You can. You can. If you are going to include QCD, you have to do it. You have to have an explicit index for the color, and then you have to take traces and all these things, and the gluons, all these things have to be taken into account. Depends on the context, right? Yeah. Maybe in a later example. There is this, in Griffiths, there's a QCD chapter. There we will see. Okay? I'm going reasonably slowly because I want to impress all these physical aspects to you. Okay? We will talk about standard model. You have to know G, you have to know GW, you have to know G prime, you have to know sine squared theta, you have to know Cabibbo angle, you have to know PMNS angles, all these things. Okay? So the best way to introduce, rather than talking in the abstract, is to take specific examples and see how each one of these enters. Okay, this is my way of doing it. There are probably better ways of doing it in some other planet. Yeah. Yes. When you write down the standard model Lagrangian, you start out with fields. Okay, you start out with gauge fields, SU2 cross U1 gauge fields. Okay. Then you introduce the Higgs mechanism. By you, I mean we, and we will do this. When we introduce the Higgs mechanism, and then we select the Higgs vacuum expectation value to be in such a way so as to break SU2 cross U1 into U1 electromagnetism. And when you do that, you see that there is a mixing. And this mixing is given by an arbitrary parameter called sine theta W introduced by Weinberg. Now you have to go to the experiment to fix the value of sine theta. Okay? So it is always a mixture of theory and experiment. When you say mass of the electron, it's a free fundamental parameter of QED Lagrangian. But to say 0.511 MeV, you have to go to the laboratory to measure. So you cannot have the strict, this kind of a distinction between theory and experiment. Okay? Did I answer your question? Everything here, standard model is a phenomenological model. It has been invented to describe phenomena. Phenomena as in quarks, leptons, their interactions, their strength. Here, I mean, this is a theoretical formula, okay? The value of GF is obtained from the lifetime, okay? And it turns out that it's the same GF that also enters into the UD bar vertex. So in the construction of the standard model, we have taken into account all these experimental knowledge that it's the same strength of the interaction, whether it is the muon or whether it is the quarks or whether it is the tau lepton or the electron. In the standard model, we behave as if these are universal interactions. But in the sphere of logic, they need not be universal. There could be a different interaction for each particle. The way you have constructed the standard model, you have made it universal. Okay? And if the logical possibility that they are not universal, that would have to manifest itself in some experimental observation. For instance, the standard model forbids the decay of a muon into an electron and a photon. Okay? There is no vertex in the standard model that allows the decay of a muon to an electron and a photon. However, at the Paul Scherrer Institute in Switzerland, there is an experiment called MEG. Why is it called MEG? Mu to electron gamma. The name of the experiment is MEG, where they are trying to see if there are any rare events where the muon beams that they have shows evidence for the muon decaying into an electron. Okay? So if it is observed, it is a violation of the standard model. That's the name of the experiment, MEG. It's an ongoing experiment. I don't know whether it is still going on. Okay? Then there are other experiments in various places. There's one called the pen experiment. Pen for pion, electron, neutron. Pen experiment. Okay. Then there's another one called pi beta experiment. A pi plus going to a pi 0, electron, neutron. Pi beta, pion, beta decay. Okay. So there are always experiments which try to check whether the standard model is right or wrong by looking for possible signals which are not allowed by the standard model. Okay. So when you say theory and experiment, these all go hand in hand. Okay, I'm needed. Actually, somebody wants me. Okay. Okay, ladies and gentlemen, thank you very much.